Hello, I'm Dave Rothery. I'm the S283 module team chair. This is just as brief as I can make it, introduction to S283, Planetary Science and the Search for Life. For those of you who are thinking of starting the course in October 2020, that's for the 20J presentation. It's 10th of August now. I'm recording this from home. Normally I'd do this video about a month earlier from my office at Walton Hall, and I take you around the campus and introduce you to other members of the module team. But there are very few people still working on site even now. I'm not allowed back on site yet. So you have to make do with this. I guess you've all been shielding and so on at home, and many of you have had your lives disrupted like we have. S283 managed to get by without too much disruption in 19J. The exams had to be done online, which worked out relatively well. But let's talk about what we're going to do this year. I can't show you my normal office, but this is where I'm working at home now. I'm going to switch this around to a forward-looking view. Just bear with me. So here's my forward-looking view. This is where it's all happening at the moment. I have dog on the floor who will miss me when I do start going back to the office. On the screen there is the 20J website for S283, and that's where you should guide yourself from. There is a course calendar. Here you can expand each week as you get to it. And this is where you will find what you should be reading and what activities you should be doing. Clicking on the reading links will open up further material. You have available to you the PDFs of each book and each chapter online as PDFs, and you also have the physical books. This screen is taking a long time to upload, but now we've got it. It depends on the speed of the internet. So this is telling you what you should be doing in the first week, and there's a link to the PDF of chapter 1 of the first book. So you will have PDFs available to you all the time you're online, but we do send you real physical books as well. These books were new 2 years ago, so they're relatively up to date. We have been updating them to remove a few fairly trivial errata and to bring a few facts and figures slightly up to date. And some of you will get the revised impression of book 1. The way to tell is to look here and see whether it says 2018 or 2020. But the changes are all fairly trivial, and you'll all have the PDFs and the errata list anyway. We will not be updating or reprinting yet the second book, though the PDF will be updated online. Okay, so what's the content of the course like? It is essentially geology on other planets, but more than geology, because there's meteorology and there's some planets with no solid surfaces anyway. And there's also looking at how different parts of the solar system could be habitable. Indeed, not just our solar system, but other planetary systems, because we know about plenty of planets around other stars now. So towards the end of the course, you're looking at planets which aren't even nearby. So let me take you through the course content, because that may be how you're deciding whether you want to study this course or not. So introduction to the solar system tells you what the solar system is like, and then what the structure of the planets is like inside. If they're rocky planets, how planetary volcanism works, planetary surface processes, cratering and wind and flowing water. Then we look at the atmospheres of the terrestrial planets. Then we look at the giant planets, Jupiter, Saturn and so on, then minor bodies, and how the solar system may have begun. And then we look at meteorites, because they're samples of solar system material, very often unprocessed, and give us a lot of good information. So you'll see it's a very well illustrated book. These are images of Mercury from a recent orbital mission of Mercury. So we're very quickly introducing you to the major types of bodies in the solar system in chapter 1. Then it gets a bit numerical when we start looking at chemical compositions of basalts from the moon and meteorites and so on. We look at how the Earth works internally. You will remember some of this from S283 if you've done that. I actually wrote the does the Earth move beneath your feet part of S283 if you've done that. Then we go on to planetary volcanism. Volcanism works in an atmosphere and when there's not an atmosphere. We look at cratering processes, ways to analyse atmospheres. Magnetic fields are covered rather briefly, just to give you enough to go on. The internal structures of the giant planets, Jupiter, Saturn, Uranus and Neptune. The layered structures of their atmosphere. Wonderful picture here, Jupiter from below one of its poles seen by Juno, which is orbiting Jupiter at the moment. Asteroids, really weird shapes. This is a contact binary. It's two objects that have become stuck together, surely. And when we talk about bodies further out from the sun in the Kuiper belt, and we look at how the solar system may have formed. So that's the first book. The second book, Astrobiology, is there because one of the main drivers for wanting to explore planets is to see if there's anything living there at all. Now, we're not thinking of complex life anywhere in our solar system, really, certainly not living at the surface, but there's plenty of little niches where there might be microbes, bacteria and single-celled organisms. So we look at basically the chemistry of life and how life may have begun to begin with. So this is recapitulating some basic biology that you might know and extending it a little bit further. So how life began, what makes a planet habitable? Does it have to be like the Earth with liquid water at the surface? Well, we do think we need liquid water, not too hot, not too cold, and the right kind of chemistry where we know life can function. But it turns out that the surface of a body is not the only place we can have the right conditions for life. You know, we look at the early Earth, we look at evidence for very early life, fossilized life and so on, and extreme environments. Inside a rock here, this is an Antarctic rock broken open, and this green gunk here is algae that are doing photosynthesis within the rock. There's enough sunlight getting through the rock. So things can live inside rocks, which is relevant when we come to Mars. Are there places on Mars where you could go inside a rock today and find single-cell organisms living? How are we exploring Mars? Here's places where rovers have landed on Mars. One member of our course team, Susanna Schwenzer, is one of the people helping design the route that the NASA Mars Curiosity rover is taking to explore the surface. So she's a great person to have on the course team. And then beyond Mars, we look at other places where there could be life, and then we start going inside icy bodies. This is a cutaway model of Ganymede, one of the moons of Jupiter. We spend more time talking about Europa, which very clearly has an ocean below its icy surface. And the question is, below this fractured ice, or periodically fractured ice, is there a niche where life can exist? Because we've got water being drawn into a tidally heated rock, coming out through hot springs, and giving an environment where life can subsist on chemical energy, totally divorced from sunlight. You do not need sunlight to power life. It can exist on chemical energy. There's some evidence of plumes erupting from Europa, but Enceladus, the moon of Saturn, has plumes that have been seen by orbiting spacecraft. So Enceladus is a great place to consider as well. So if you want to find life present in the solar system, you'll look inside Enceladus or inside Europa, or more conveniently, you'll fly through a plume of ice particles erupting through one of these fractured icy surfaces, bringing oceanic material into space. You don't even have to land to sample the chemistry of life. We'll look at Titan as well, an icy moon of Saturn with an atmosphere and methane rain filling in these lakes of liquid methane. Wonderful place. Then we look at planets around other stars, and we see how the brightness of the star dips when the planet passes in front of it, and that dip there is 0.15%. It's a tiny dip. That's a Jupiter-sized planet coming in front of a star. The dips when Earth-sized planets are much smaller. But that's one way we can learn about exoplanets, is when they go in front of a star. We also have the orbital motion of one body going around another. Even though the planet is less massive than the star, the planet does tug the star to and fro a little bit. And so you get changes in the radial velocity of the star. So by measuring the star's radial velocity, by looking at its spectrum, seeing how the spectral lines shift to and fro with a Doppler shift, you get information about orbits as well, and that's what this kind of data is all about. So we've learned a lot about exoplanetary systems, and we look at how those compare with our solar system, and whether they might be habitable either at the surface like the Earth, or maybe underneath some ice like on the moons of Jupiter and Saturn. And we finish off with looking at how we might find if this kind of life does exist. Has it affected the atmosphere of the planet, and so on? What clues will we get from the James Webb Space Telescope, which we're still waiting to be launched? That will give us some clues about atmospheres of exoplanets. And then how do we find out about extraterrestrial intelligence? We look at the work of Carl Sagan and Frank Drake and so on, and how we might try and signal our presence, how other civilizations might be trying to signal their presence. It's a fun course. A lot of geologists are reluctant to take it because they fear there's too much maths in it. It's not actually that complicated mathematically. If you don't like equations, there's some bits of the course towards the end that you might not be comfortable with. But when it comes to exam time, you can bypass those questions and concentrate on the others. If you're okay with maths, more of it is open to you, but you might find the geology a little bit outside your field of interest. But geology is great, for heaven's sake. You're melting rocks, blasting them up into space for eruptions, or melting them and spreading them across the surface, or deforming them. Geology is a good subject. You should not shy away from it. So it's a course with something for everybody. The course website is here. It's being a bit slow at the moment. Let me show you last year's, because there's quite a lot of discussion in the forums. Let's go to the forums. We had a very lively discussion forum between students last year, and I do hope you will take part in this. If you take the course this year, and I've chosen to record this on the day when the OU website isn't playing ball. So if that opens, I'll show it to you. So basically, I'm going to give you a link to last year's introductory video as well, which is a much fuller one, and you can see more people than just me. If you enjoy planets and enjoy astronomy, it's a good course for you. It's a 30-pointer. That's a little bit unusual. You need to find another 30-pointer to go with it, because eventually you'll need 120 points at level 2. A lot of students take the astronomy course. That was S282, it's now 284. Other 30 pointers in science are biology of survival. I think that's S293, which goes quite well with the astrobiological aspects of this course. So there are ways to include this course in a BSc degree. Okay, the website has finally responded. So let me just show you the module forum, which of course that's going to take ages to open now since it's misbehaving. But take my word for it, module forum, very busy. Okay, it's opening. And okay, there's people talking about the exam results, and we announced the prize winner. There is a prize for the student who does best in the exam, and a lot of discussion going on all through the year. This is one page out of how many pages did we have in the end? Just in the main forum, come on. Oh well, more than 5 pages of discussion of threads we had there. So a very lively forum. The exam. Let me say a little bit to you about the exam. The exam is not meant to be a memory test. It's far more important that you're able to show that you understand things. Now, last year's exam was written to be done in 3 years in an exam hall. In the end, we had to offer it online with 24 hours to answer it, with access to all the books. So it turned out to be somewhat easier because, of course, if you have got reference material, you can find some answers without really understanding quite so deeply. But anyway, we'll see how the exam is able to be offered this year. We don't know yet, but the exam format will still be like this. There's a specimen exam paper which you can find on the module website, and there are answers to that as well. So let me talk you through the specimen paper. There are 3 parts to the exam. Part 1 is computer marked. There are 8 questions. It's multiple choice. Well, this year it wasn't computer marked. We just said write your answers down, and we'll attach it to your electronic files for the rest. But short answer questions. Then there's part 2, which is 4 questions. You choose any 3 of them, and they're based on book 1, Introduction to the Solar System. Then part 3 is another choice of 3 out of 4 questions based mainly on book 2, Introduction to Astrobiology. So let's have a look at these questions. Scroll past all the general introduction stuff. That's the computer readable form if you need to use it. Okay. Question 1. What's the distance of Uranus from the Sun? Is it 5, 10, 20 or 30 astronomical units? And I use the Earth-Sun distance well. You should know the scale of the solar system. You have got to know that it's 30 AU out to Neptune. Therefore, Uranus is going to be 20 AU. That's the right choice there. And what are its clouds made of? So that's some knowledge required there. Here's something about true and false statements. Is decompression, melting and temperature rise the 2 main processes that cause Earth's mantle to melt? Well, actually, decompression, melting, yes, but not temperature rise, so that's wrong. So you've got to know how the Earth is working there. This question is about which bonds you couldn't detect by infrared spectroscopy, for example. Here's one that relies on you being able to calculate properties of an orbit, knowing certain parameters of an orbit. This is asking you to understand the tree of life. What does it mean? Whoops. This is a question, it's based on a figure you've seen in the book. In fact, Mars's axis wobbling around and over time. So we show you this figure and say and ask you what does it show. You should remember it from the book. Basically, it should be familiar to you. This is a question about detecting exoplanetary systems and how we'd look for intelligent life, what wavelengths to use. And this is a question about exoplanetary systems, about relationships between migration and different phases of early stellar life and so on. So, part 1, short questions with answers that cover the whole range of course materials. Okay, going to part 2, question here, it's question 9. These days it tends to be question 10, doesn't matter though what order it's in. It's a question asking you to look at some data and plot them up. So if you can use log linear plots to plot concentration data on, you can do most of this question here. Understand what these elemental profiles are showing us. That's a pretty standard question, kind of which we use pretty much every year. Question 10 is asking about the solar system. So it's giving you some text to read and then asking you to understand it. There's a question here based on a diagram. What are these layers within the Earth? Pick them off the list that I've just scrolled by, so that's understanding that diagram. This question is about atmospheres of terrestrial planets. Name the regions in the atmosphere below the exosphere and show how the temperature varies with increasing altitude. Which layer is unique to the Earth? What does adiabatic lapse rate mean? So that's about atmospheres. Final question in that part is about meteorites. What are chondrites and achondrites? What are long period comets? And what's this diagram here telling you? And part 2, so we had to answer 3 out of those 4 questions in part 2. Part 3, 3 out of 4 questions. What is it about carbon that makes it a key ingredient of life? What's a biomarker? Give examples. Why do we now discount comets as the major sources of the Earth's water? About panspermia. So short answers that add together to a long question. Talk about planetary protection. That's how we try to stop us contaminating other planets and avoid contaminating the Earth by bringing samples back from other places to the Earth. And there's some ethical issues to discuss there. How do you sterilise spacecraft? 2 more questions to go, aren't there? Okay, this is about, you saw a diagram like this in the book a moment ago. A light curve when a star is partly obscured by a planet passing between it. What's the size of the planet? You can work that out relative to the star by the dip in the light curve. And the final question, describe the Drake equation, how it can be used to argue that intelligent life ought not to be rare in the galaxy. And how does that give rise to the Fermi paradox? Describe the Fermi paradox. And Fermi paradox is, well, if there's lots of life, why haven't we found it yet, basically? So that's the end of the paper. 3 hours to do it if it's face to face. If it ends up being online like this year, you've got 24 hours to answer it. Think about the course. I hope it's the right course for you. If it's not, don't do it. But it tends to be a very popular course with those people that have taken it. So I hope to be seeing you on the course in October this year. Okay, bye.